again. My name is Steve Hillis, and this is one of a continuing series of short videos on methodology and sociology. This one's going to focus on sampling and external validity. Sampling involves how you go out and select and recruit your subjects. It focuses on who you study and how you went about selecting them. That's closely related to the issue of external validity. External validity is not the same thing as internal validity. Recall that internal validity is all about the logic, the rigorousness of your research, whether your research is really testing theories, whether you can make sense of your results and so forth. That's internal validity. External validity is a different issue. External validity deals with the issue of whether you can generalize your results to other groups of people who were not studied, whether you can generalize your results to some larger population of people. If you can, that can be a very important thing, because after all, you can study a few people and then you can talk logically, generalizing your research results, about a much, much larger population of people who you never studied. That's cost efficient, it's a powerful way to do research, and frankly, it may be a critical issue when you're studying large-scale social phenomena like sociologists do, because realistically, we can't study everyone. We can't even study most people most of the time. We can only study much smaller samples of people. And then the question is are the people we're studying really similar to larger populations that we're really interested in? That's the critical issue with external validity. And research with good external validity will allow you to generate what we call representative samples. Your samples will, in various respects, be similar to or look like, behave like, have similar characteristics as much larger populations of people, and there's a good solid empirical and logical basis to say, hey, I found it for these people, this is how I sampled them, so it's fairly safe and reasonable to generalize those results to vast numbers of, say, Americans who we never studied. Now, the whole trick or key to how good your external validity is, how sound a ground you're on in terms of being able to generalize to larger populations will depend on whether you use random or non-random sampling techniques or designs. Non-random samples a lot of times can be very simple and straightforward, and in some cases they may be completely appropriate, but you can't generalize safely to any larger population. What is an example of a non-random sampling design or technique? Well, it could be simply allowing subjects to volunteer for your research, putting an ad in the newspaper or on the internet, and then having self-selection, volunteers. Exactly because your subjects are selecting themselves into your research, well, what about the people who read the ads who didn't volunteer? They may very well be different than the people who did volunteer. The result is that you're not really on a sound foundation to be able to generalize your results to a large number of people simply because your subjects chose themselves. In other words, it was non-random. Now, another example of non-random samples would be a convenience sample. Say, for example, I would use my own students in my class to do research on. Now, that might be convenient for me. I have kind of a captive audience. If I could get through human subjects committees and get approval, then basically I'd have a whole bunch of subjects to use for my own research. But those students wouldn't be a random sample from any larger population, not even from the larger population of students at Purdue University, much less a random sample of college students in general or young people in general. So what I found by researching them might or might not apply to any other group of people in the entire world. So, non-random samples are a lot of times cheap, convenient, they have advantages, but they tend to be severely limited in terms of external validity. On the other hand, you can use random sampling techniques or designs, and there, if you do it right, with a little luck and a lot of hard work, you can create representative samples, you can have highly generalizable results. The trick is selecting your subjects from some larger population, selecting them at random. What population? You as the researcher get to choose. There's no single way of doing random sampling. And frankly, you get to select which group of people or which population you want to draw your subjects from and who you want to generalize your results to. Once you've made that choice, you somehow pick people out like ping pong balls out of a bucket. The bucket of ping pong balls is your population, and then somehow blindly and randomly you pick them out. Every ball has an equal chance of being picked, and every subset of balls in the jar or bucket has an equal chance of being picked. If that's the case, you will have just performed a random sample. Now that assumes that, well, you somehow have a list or have some way of contacting everyone in your population, and it also assumes that everyone you contact will participate in your research. What I've just described to you is called a simple random sample, which, by the way, is a very powerful technique in random sampling, and a lot of methodologists believe that it may, in many respects, be the most powerful sampling technique in terms of external validity. But at least I want to mention that there are other alternative strategies for random sampling. For example, we have what is called stratified sampling. In that case, you break your population into various subgroups. It could be based on ethnicity, race, gender. You get to pick your population, and you get to pick what strata or categories to sample. The point is you might undersample some groups and oversample others. In essence, you're doing a variation of random sampling, but you're taking certain subgroups and you're sampling many of them, and at the same time you may be undersampling other groups, and you get to decide how to weight those samples. A lot of times stratified sampling can be very effective when you can't do simple random sampling for a variety of reasons, or you're not confident that simple random sampling is actually going to work. Sometimes a second best alternative, which actually may be a lot more practically useful, is using stratified sampling. There's other variations. There's something called cluster sampling, where, for example, you might take a map of a city or a town, chop it up into grids, and then randomly sample different locations in the city. Then, within those individual grids, you might randomly sample residences or households, and then you might send out researchers to knock on doors. Now notice, you're not really randomly sampling households, and you're not really randomly sampling every individual in the city, but you're still engaging in some sort of random process of selecting subjects. We're going to focus much more here on simple random sampling because it's a very common technique, a powerful technique, and it allows us to really boil down some of the basic issues that we're going to talk about. In particular, let's talk about sampling error and sampling bias. These issues come up with any kind of random sampling, but we're going to talk about them in terms of simple random sampling, where you have an entire population, you have a list of them, and then somehow you randomly pick your sample. Everybody to begin with in your population has an equal chance of being picked. You randomly select them, and you go on from there. Now, sampling error occurs by chance. Anytime you do anything random, sometimes you get weird, fluky, unusual results. In other words, sometimes you try to do a random sample, and you don't get a representative sample. Your sample, even though you use random sampling techniques, looks very different from the general population that you want to generalize your results to. So for example, let's say that your population has roughly 50% men and 50% women, roughly 12% blacks and roughly 70+% whites. You might pull out a sample where 80% of your sample was women. And you might pull out the same sample and maybe 40% of your sample was black as opposed to white. That sample, in important ways, is obviously different than the general population that you're trying to represent and trying to generalize towards. That can happen just by dumb luck. There's a reason we call this sampling error, because it does involve literally white noise or error, randomness. Now, that can create problems because, well, again, The whole idea is to generalize representative samples and get good external validity. And sometimes just by dumb luck, you get samples that are really screwy and non-representative. The good news here is that first of all, you can get a sense of how likely that is. At least you can quantify the likelihood that you're going to get an unusual non-representative sample. But another point that needs to be stressed here is that there's a very simple, straightforward solution for dealing with sampling error, and it's a very powerful one. Just increase the size of your sample. It turns out that sampling error on average declines dramatically as sample size goes up, very quickly, very dramatically. So, if you sample 500 people and you're really worried about sampling error, sample 1,000 or 1,500. What's amazing about statistics and sampling is how quickly sampling error declines as you increase the size of your random samples. Even with samples of 1,000 people, sometimes even fewer people, you can be moderately safe in generalizing to populations of millions and millions and millions of people that you never studied. Now, is it possible that you could pull out a sample that was really screwy and weird? Yes. But if that's a serious problem or a serious concern, increase the size of your sample.